In this video, I'll be showing you how you can create every single city on the planet in under 10 seconds. I'll be going over how you can use completely free datasets to plot all the cities of the world. There's about 48,000 cities here, all plotted. And not only will we take a look at how we can do that through blueprints, we'll take a look at how we can keep the performance for that process fast. I'll start off with a brand new project, but before we really get started, we'll have to make sure we get our data for where those cities are located on the planet. There's a lot of great resources out there for free data. There's OpenStreetMaps, which has street data. There's a site called heightmap.skydark.pl, which has a lot of height map data. There's a site like Open Topography, which has a lot of data of landscapes. But the one we'll be using today is simplemaps.com, and you'll see that they have a basic database for world cities. And it's freely available to download, and it has about 47 or 48,000 places located in that data set. Once you've downloaded that data set, if you open it up and take a look, it has all the cities in here with their name, their latitude and longitude, which is going to be the important information for us to find out how to position these. But there's also other things in here like population as well and some other data. And there's a lot in here. Like if we take a look at how many cities we really will be plotting, it's about 47,869 cities. So once we have this data set, we can start taking these latitude and longitude values and using those to create and position these points or objects in 3D space. Now that we have that data, we have to figure out how we can use that latitude and longitude to plot our points or create our points and position them in 3D space in Unreal. The coordinate system in Unreal or 3D softwares is very different from that of latitude and longitude. Latitude and longitude is not Cartesian 3D space. It's not going to be the same. It's meant to be structured around a planet or a sphere. So it's a little bit different. And this is kind of how latitude and longitude works. You have your two axes. Let's say we have our horizontal lines here, which is latitude, and then our vertical lines here, which is longitude. Now, the vertical line, this white one that we see, is pretty much the 0 point of it. And these values go negative and positive. So anything west of the longitude 0 point here, which is actually the prime meridian, it's an arbitrary kind of point or position vertically on the planet they chose to represent pretty much the 0 axis of the latitude and longitude coordinate system. So anything west of that line becomes negative or is referred to as west. And anything east of that line is positive or is referred to as east. And same thing for latitude. The latitude line, its 0 point is the equator, pretty much halfway from the Earth's bottom to the top. And that 0 line or the equator, anything below it is negative or south, anything above it is positive or north. So where these two lines meet, the prime meridian and the equator, that's exactly the 0 point of the coordinates for latitude and longitude. And again, anything west is negative, east is positive, anything south is negative, north is positive. So that's kind of how the coordinate system works for latitude and longitude. And we'll have to translate that into the 3D space we have in Unreal. Now, if we do a little bit of homework and we know how to draw some circles using math, we can slowly start to figure out how we can kind of create this latitude and longitude plotting in proper 3D space, in X, Y, and Z, in more of a Cartesian coordinate system. So what I have here is the X and the Y, and you can see them drawing these lines or just tracing their positions. And I have the radians here go from negative all the way up to 0 and then to positive. And that's pretty much the same as if we had negative 180 degrees to positive 180 degrees, and we could see what happens. But these are not showing as degrees, it showed as radians. And you can see my formula here is just 1 times cosine times sine, and then for the y-axis, it's 1 times cosine times cosine. And that 1 is the size of the sphere. So using this formula, we're going to be able to plot the x and y, or the latitude and longitude, in 3D space properly around a spherical shape. So now we can start putting this into practice. So the very first thing that I'm going to want to do is to get my database into Unreal. We're going to have to read out that latitude and longitude before we really can do anything. So the very first thing I'm going to do is right click, and I'm going to create a blueprint structure. So I'm going to go here to blueprint structure, and this will be what we're pulling from our database. And I'm just going to call it f underscore cities database. And we'll open that up. And this is where we're going to be able to add what datas we're pulling from that database. So if I quickly just jump back to our CSV file, or that data file with all the cities, we have lat and long, and we want to use this exact spelling. So lat and LNG. So I'm going to go in here and create lat, and I'm also going to add LNG, and we're going to set these both to floats because they are numbers with decimals. So we don't want them to be an integer. We want them to be able to have decimal places. So we'll set them to a float, and then we'll save this. And once we've done that, the next thing that we can do is actually bring in our CSV file or a database. And if you want any other information, you can just add it in here. So if we even added, like, what else can we add from here? It might be useful. The country or the city. So maybe city would be good. So you can really add whatever kind of data you want, country, and that would be text. So it'd be like a string. I guess you could do text as well, but I'll do string, and we'll save that. And I will close this and then import our CSV file or our database. So I'm just going to drag that in here. There it is. So we're going to import in as a data table and choose what kind of structure or row type it's going to follow, which is going to be our F cities database. And we'll click apply, and it might give you a bunch of errors because maybe there's duplicate rows, or there's things that we're not loading in, but we can probably ignore those and just click OK and see if it worked out by just opening up our world cities data table here and seeing if it actually pulls out our values. And it seems like it's working here. I see latitude, I see long, I see the country, and I see the list of all the different places. So if I choose one of these just randomly, it gives me the latitude and longitude, so I know that's all working. So now we have our database or our data table, and then also our structure pulling out information from that data table. So next we'll create our blueprint. We'll right click blueprint class, we'll make it an actor, call it BP underscore earth. And we'll open up our blueprint. We'll go to our construction script because we want to create all these points. And we only want that to happen once. We don't want that to keep happening as we're playing. So it makes sense for it to be in the construction script. We'll also go up here to class settings and turn off this run construction script on drag just so it speeds things up if we have to reposition something. I don't think we'll need that on, so I'll just do that for now. And then we're going to have to add our component, the thing that we want to plot for our cities locations. So I'm going to add I'll add a hierarchical instance static mesh, but that or an instance static mesh would be suitable. You definitely want it to be instanced when there's so many points. And then for the mesh, I'm just going to choose, let's see what we got in here. I think we have some spheres in here. So I'm going to choose sphere. I'll just search. What do we got? So there's a lot of stuff in here. Here we go. I'll use the S1 unit sphere static mesh. So I'll select that. And then we could also attach material to that as well and throw that in here. But for now, I think this will be fine. I'm just going to have the mesh, and I will compile this. But later on, if we want to, we could pop in a material here as well. So we'll start off by dragging this construction script out and creating a get data table row names node. And we'll be able to select our table, so it's going to be the world cities, and that will get us a list of all those entries in that table. So the next thing we want to do is loop through each one of those rows. So I'm going to drag this pin out and do a for loop. And we want to do not for each, but just for loop. So where it says flow control, we can just do a for loop, and that will give us access to what entry do we start on, what entry do we end on. We don't really know exactly how many rows there are in that data table. Like, we could go check, but it'd be nice if we can get that automatically, which we can do here. So when we get the data table row names, we can get all the row names as an array. We can get the length of that array and feed that into our last index, and it will now do a loop of however many entries there are in that table. Now, this would be great for when we want to plot all the points, but for now we maybe just want to test and only plot like a couple hundred points instead of several thousand or tens of thousands. So I'll leave this disconnected for now, but we'll reconnect it later. And for now, we'll just do a test of maybe 500 points or 500 locations we're going to plot our object at or create our object at, just as a test to make sure it's working. So from here, we need to get the latitude and longitude values so we can use that to place our objects at the correct location. So on the loop body here of our loop, I'm going to drag this out, and we're going to get data table row under utilities here. We'll choose our world cities data table. Now it gives us all the row names. So we want to make sure we're getting the right row name so we can get the latitude and longitude for whatever that name is. The problem is we'd usually do that with our index, but we can't plug our index. Our index is what loop we're currently on. What kind of item are we processing between this first index and this last index? So we would ideally want to use that, because in that case, 0 would be Tokyo, 1 would be Jakarta, 2 would be Delhi, and so on. So it's all in order, but I can't connect that index to here because this is a number and that is a name. But what we could do is use our out row names here, because that's an array of all those names, same as this, just all those names stacked in order. So what we can do is drag out our out row names over here and search with context sensitive on get, and we can get a reference or get a ref. And then what we can do is use that index to pull out that name, and then that will match up here and we can connect that in. So now we can properly pretty much cycle through all those row names and then be able to pull out the correct data over here. So this is the rows within that that row, like whatever city we have chosen. This out row is going to have the additional information like latitude and longitude. So we can right click on that and split the structured pin, and now we have the latitude, longitude, and even the country we also added to our structure, so we see that as well. So now that we have this info, we can start using this. We can start using the latitude and longitude of that city to actually place our object at that point in 3D space. And this is where that math will have to come in. So if you remember our formula, or that kind of equation that I showed a bit earlier, it's a size of the sphere. So let's call it planet size multiplied by cos, and then the latitude as a radian multiplied by cosine longitude as a radian. So to do that, I'm going to start off with the very first thing, our planet size. So I'm going to add a variable here. I'm going to call it planet size and make that a float. And I can just drag that into here, hit compile, so I can actually place a default value for it. And maybe we'll start off with something like 100 for its size. And there we go. We got our planet size. Now the next thing we have to do is do the math to get the proper location for the latitude and longitude in 3D space. So we're going to take out our latitude and longitude. And if we need to convert these from degrees to radians, we'll have to do a little bit of math. Again, our data table has them here, latitude, longitude. It's resembling them as a degree. So we have to actually turn them into radians. And to do that, we could essentially multiply it by pi divided by 180. So that's one thing that you can do. You can do that conversion. However, Unreal does have the ability where if I create a cosine or sine node, you have the ability to use radians or degrees. So maybe we don't need to do that conversion to radians. We can just use the cosine and the sine nodes that work with degrees. So that might just save us a little bit of creating nodes and stuff. So we'll do that instead, just to make it a bit more simple. So I'm going to drag out the out row latitude, and I'm going to connect that to cos, but make sure it's cos degrees, and it'll show it as cos d. If it wasn't using degrees, it would just say cosine or cos. But since this is the version of the node that is expecting degrees, it's called cos d. So I connect a cosine node up to my latitude. Same thing for longitude, another cosine node. Then the next thing that we're going to do is multiply both those together. So I'm going to multiply. There we go. Multiply them together. And then finally, we'll take our planet size and multiply that like that. And this gives us our x position. So if we think about the formula for that, it's planet size, or whatever our formula was. In the sample I had, it was 1, but it's our planet size multiplied by cosine latitude by cosine longitude. And now for the y position, it'll be a little bit different, but mostly the same. Same thing. We multiply the planet size, but this will be the y position. So y position is planet size multiplied by, again, another multiply node. But instead of 2 cosines, what we're going to multiply is the latitude cosine by a sine. And again, we want to use degrees, sine degrees, by sine of longitude. Like that. And then finally, our z position is going to be the same thing, planet size multiplied, and this will be really easy, just sine into our latitude, like that. We don't need any other multiplication. That's pretty much it. So now we have all of our conversion from latitude and longitude to XYZ positions. Now most of the hard work is done now. Now we just have to plot our points. So we're going to take our object, or our point here. It's just the sphere that I chose here. So hierarchical instant static mesh. I'm going to drag that into here so I can use that. And what we're going to do is we're going to drag that out, and we're going to do a add instance. And we'll connect that to, when the row is found, the next thing we do is add our object to the location of our latitude and longitude. And what we're going to do here is we have to have an instance transform. That's where it's going to move this instance of this object. So for that, we can split this pin, split that pin again, and now we have our X location, Y location, Z location. Really easy. And that's pretty much done. So let's compile this. Let's see what happens. If I click compile, compiles in 138 milliseconds. Let's look at our viewport here. Wow, look at that. We got points. We got points on our sphere or on our planet. So really cool. So let's try this with a lot more points. Let's go in here back to our construction script. This seems like it works. So let's try using the full length, all 47,000 points. So I'll connect that up and then I'm going to click compile. Okay, so now it's something that we all feared would be a problem. I can see down here that to compile this, and I paused the video while doing that, it took 242,000 milliseconds. So 242 seconds to grab all those latitudes and longitudes and plot our objects at those locations converted into our 3D space. And that's not too long, but for 47,000 items, having to wait 242 seconds, it's a little bit of an inconvenience. It takes a bit of time. So I think we can get that performance better. Like if I look at the viewport now, it might take a little moment to load, but then should be pretty quick. There we go. So there's all our points plotted, or all of our objects placed. And maybe those objects are too big. It's almost like making the landscape as well. They're overlapping too much in a lot of locations, as you can see. But it works. But I think we can get this performance a little bit better. And one other thing that we will notice too is if I'm looking at this, it feels a bit off. It feels like when I'm looking here through it, that's correct. But it's like mirrored. It's like everything's backwards. So maybe something's a little bit odd in my calculation for this positioning of these points. And it's not a major issue. It's just something needs to be flipped around here. Now, before we fix that mirroring issue, let's first get our performance to run a lot better. So very first thing we're going to do is I'm going to go over here and disconnect this last index and set it to 500 just so we could test quickly. And then we'll get rid of this add instance node and instead of that, use something called add instances. And that will allow us to add all the instances based on an array of transforms, which will perform a little bit better. So we're going to take our execution pin here, connect that all up, and then we can't connect our XYZ positions to this because this is looking for an array of transforms. So we have to build a transform and then build an array of transforms. So first I'll go in here and right click and do make transform. We'll split the location, connect it up to our X, Y, and Z. Now we have our transform. Next, I'll drag out that make transform and I'll do make array. And now we have our array. So now we can connect that array to our instance transforms and we can test this out. So to test this out, if I click compile, it took 139 milliseconds. But the problem is this is still only doing 500 items. Let's move that up to 5,000. Let's try this again. So if we go here and click compile, now we're waiting and took 3,000 milliseconds. So 3 seconds. So not that fast. One thing you can also do to improve performance is turn off this update navigation. We probably don't need that to update. And now if we click compile, okay, now it's 453 milliseconds, much faster. So that's a lot quicker. 453, 449, 447. So already a big improvement. Now there's one other thing we could do if we wanted to store these transforms in a variable to access somewhere else. You could essentially do that as well. And an example of that is I could just add a variable here. I can call it something descriptive of our transforms. Maybe let's call it like instanced or instance transforms and set it to a transform. But I need it to be an array, so I can click on this and switch it over here to be a array. And then what I technically could do is bring this in here, set it, and connect that up. And that might be useful in a lot of cases. But if we look at this right now, if we click compile, again, 487, 452, 451. If I connect this up, I don't think that should hurt the performance if you did need to do that, but we'll test it out just to make sure. So if we connect that in there, maybe I'll restructure some of this graph to be a bit nicer. There we go. If we compile this now, 466. So now let's try this with our full data set. So instead of 5,000 points, back to our full length. And let's give that a compile. So I'll clear this and I'll click compile. And we're waiting. How long does it take? Hopefully, there we go. 4,924 milliseconds. So under 10 seconds. So from 242 seconds to 4 or 5 seconds. And maybe that was just lucky. If I compile again, let's see how long it takes. So 5 seconds. So 5 seconds for our 47,000 positions. And if we go in here and change our scale, maybe 0.25 would be better. These spheres are much too big, or maybe the world scale needs to be bigger too. So maybe I'll go in here to our construction script and our planet size, I'll set it to 500. So it just makes the planet much bigger. So those points are more spaced apart. So let's see how that looks. And that looks much better. Now we start to see all that detail. Now, things are still inverted. So let's quickly fix that. I probably could restructure some of this, but I think the easiest way from looking at what was going on there, we just need to flip our Z position. So I'm just going to do a multiply and multiply our planet size by -1 as a bit of a quick fix, and then only do that for our Z position multiplication here. And if I do that and compile, and we take a look at this in the viewport once it compiles. So 5 seconds to compile, not too bad. Now, does this look right? If I flip it upside down, it looks right. Things aren't mirrored anymore. I see there's like, North America here, and then South America, and then we got like Africa, India, and the rest of the world here. So this all seems to work. So it is upside down, but I could just place that in my scene and rotate it 180 degrees and it would be fine. So I'll leave it there, but could be a couple more things you could work on, fix up, maybe add some interesting material to this as well. And then you can kind of get a look at what we had at the start of this video, where I kind of demoed what happens if you do put on a simple material and present it in a little bit better way than just the blueprint viewport here. And just to go over that very quickly, if you were to create a material, let's call it like m_cities, and I just gave it some emissive color to glow, and we apply that to our material here. So instance static mesh, let's bring in that m_cities. So now we have a proper material on there, and we drop our planet into our viewport here, and then we'll reset the positioning, rotate it 180 degrees, and then we should be good. So here it is, and we go on here, and we'll just rotate it 180 degrees, and then reset the location. And there we go. Now we have our planet here. And if we take a look at it, there's all of our points. If you enjoyed this video or you learned something new, don't forget to like and subscribe. And if you are part of the Patreon, which you can find a link to down in the description below, you'll also get access to the PDF for this video, which goes over all the steps we went over in this video in a little bit more detail.